August 17, 1942. Over the French port city of Rouen. The first American heavy bombers entered European airspace in daylight formation. 48 Boeing B-17 Flying Fortresses from the 97th Bomb Group advanced at 23,000 feet. The air temperature outside measured -30 degrees Celsius. Engines held steady at 2,500 revolutions per minute. Each aircraft carried approximately 2 tons of bombs. Below them, occupied France stretched in geometric farmland, rail lines, and smoke columns from earlier Luftwaffe alerts. Weather reports described high cirrus layers with intermittent visibility at 12 kilometers. The formation flew in combat box arrangement, 3 squadrons of 16 aircraft each. Intercom chatter remained minimal. Every crew position reported operational. The B-17E airframe weighed 54,000 pounds fully loaded. For Wright R1820-65 engines provided total output of 4,800 horsepower. The aircraft's fuselage carried 13.50 caliber Browning M2 machine guns. Each was mounted in paired turrets, waist positions, nose, and tail. Ammunition load exceeded 6,000 rounds per aircraft. The defensive field of fire covered nearly every approach angle. Ground radar stations in Normandy identified the formation shortly after 1,000 hours. Luftwaffe control at Abbeville scrambled fighters from Jagdgeschwader 26, equipped with Messerschmitt Bf-109G-1 interceptors. Japanese military observers attached to the German Air Ministry, then stationed in Paris, were informed of the mission later that day through liaison channels. Reports indicated curiosity and skepticism toward the American design. In Tokyo, aviation journals had previously dismissed the B-17 concept as an overbuilt, inefficient fortress. Editorial commentary suggested that concentrated firepower reduced range and agility. Japanese officers studying European developments considered the bomber's performance incompatible with Pacific conditions. The Rouen raid would provide the first real test of those assumptions under full-scale combat. At 1,027 hours, the lead bomber, commanded by Colonel Frank Armstrong, released its payload over the rail marshalling yards. The release altitude registered 22,500 feet. Bomb fall time averaged 38 seconds. Below, explosions struck rolling stock, warehouses, and the freight terminal. German anti-aircraft artillery responded within 45 seconds, firing from prepared 88mm batteries. Fragment bursts filled the sky at the formation's level, but spacing and altitude discipline prevented major disruption. The first interception occurred 3 minutes later. For Bf-109s approached from the sun, diving from 28,000 feet at a speed of 650 km per hour. Tail gunners opened fire at 800 meters. Tracer lines intersected across the attackers' paths. One fighter broke formation and descended trailing smoke. The remaining 3 passed through and climbed to reposition. Radio logs from the 340th Bomb Squadron noted over 20 fighter passes during the return leg. Ammunition consumption averaged 65%. 2 bombers sustained minor structural damage but remained airborne. Gun cameras confirmed at least 2 enemy aircraft destroyed. For many Allied airmen, the raid represented proof that precision daylight bombing could be achieved with disciplined formation tactics and mutual defensive fire. At Abbeville Airfield, German officers examined bullet-damaged fighters and documented the pattern of .50 caliber impacts. Reports forwarded to Berlin highlighted the unexpected density of the B-17's defensive arcs. One pilot described the engagement as flying into a crossfire from all directions. Japanese observers reviewing the same documents later translated the phrase as lead curtain. By evening, aerial reconnaissance confirmed successful destruction of the Rouen target area. Allied Command declared the operation the first operational test of the Flying Fortress over Western Europe. In Tokyo, technical attachés received microfilm copies of the German assessment. Their preliminary comment noted disbelief that an aircraft so large could sustain formation under such defensive stress. Yet evidence suggested otherwise. The B-17 had survived concentrated interception with minimal losses. The opening phase of the air war over Europe had introduced a new principle, that survival in daylight bombing depended less on speed or maneuverability, and more on coordinated, overlapping firepower. For the Japanese military attachés observing from a distance, the American design now demanded renewed attention. But Flying Fortress concept was no longer theoretical, it was operational, measurable, and evidently effective. By early 1943, reports of the B-17's performance circulated widely through Axis intelligence channels. The Imperial Japanese Navy Air Technical Department in Yokosuka received translated German combat analyses describing the aircraft's durability and defensive system. Comparative data tables listed engagement ranges, ammunition expenditure, and gun coverage angles. The findings conflicted with pre-war Japanese doctrine, which emphasized maneuverable bombers with minimal defensive armament. Japanese air planners noted that the B-17's armor distribution differed from their own bombers, such as the Mitsubishi G4M Betty. The G4MS unarmored fuel tanks and absence of self-sealing technology prioritized range over protection. In contrast, the B-17's 3/8-inch armor plating around crew stations and self-sealing fuel cells reduced vulnerability to incendiary and tracer rounds. Field tests indicated that a direct hit from 20 mm cannon fire often failed to destroy a B-17 outright. Allied mission records confirmed this resilience. In raids over Germany and the Netherlands during late 1942, loss rates for B-17 formations averaged 4 to 6% per mission, significantly lower than those of British Wellington or Halifax bombers flying at night. Japanese intelligence summaries noted the correlation between survival rate and gun placement density. Each B-17 carried twin-gun turrets in dorsal, ventral, and tail positions, coordinated by intercom to prevent firing overlap. In March 1943, Imperial Navy engineers obtained further information from German sources. Technical Attaché Commander Junpei Tsukuhara, stationed in Berlin, reviewed captured airframes and flight test data from downed fortresses. Measurements confirmed the accuracy of Boeing's published specifications. The wingspan extended 31.6 meters, the bomb bay carried up to 4,500 kilograms, and operational ceiling reached 35,600 feet. The German evaluation emphasized structural redundancy. Each major system had multiple backups, ensuring continued flight after partial damage. At the same time, Japanese airmen returning from operations over Guadalcanal described the vulnerability of their own aircraft under American defensive fire. Encounters with B-17s and later B-24s during attacks on Henderson Field resulted in heavy losses. Observers reported that even when approaching from blind spots, the bombers' overlapping defensive arcs forced attackers to break off prematurely. Post-mission debriefings included comments such as "approach window closed after 3 seconds of exposure." American gunnery manuals later captured by Japanese intelligence explained the rationale. The zone defense method divided each bomber formation into interlocking fields of fire. Crews trained to coordinate bursts, creating continuous coverage zones at distances between 300 and 800 meters. The strategy required discipline but reduced individual gunner fatigue and maximized ammunition efficiency. Production figures further illustrated Allied commitment to the concept. By mid-1943, the United States had produced over 4,000 B-17 aircraft. Factories in Seattle and Wichita operated on triple shifts. Gun installations were standardized for rapid assembly. Every fortress left the line equipped with at least 13.50 caliber weapons, powered turrets, and electrically driven sighting systems. Spare parts were crated for overseas deployment within weeks of assembly. Japanese naval staff interpreted these figures with concern. Internal memoranda from the Combined Fleet Technical Bureau predicted that mass production of such heavily armed bombers could overwhelm defensive patrols. Calculations estimated that intercepting a full formation of 50 B-17s would require at least 100 fighters in coordinated attack waves, each making multiple passes under concentrated return fire. By late 1943, the Imperial Navy initiated analytical studies of defensive gunnery effectiveness. Simulated engagements conducted at Yokosuka using target drones and mock gun positions demonstrated the effect of interlocking fire. Test results confirmed that even moderate-caliber weapons, when properly coordinated, produced high kill probabilities against fast-moving interceptors. The study concluded that the B-17's design represented an evolution in air warfare, an aircraft built not merely to deliver bombs, but to survive in contested airspace through collective firepower. These findings reached Japanese frontline commanders in early 1944. Many pilots dismissed them as Western exaggerations. Combat veterans, however, began to reconsider. Reports from New Guinea and the Solomon Islands described the growing presence of flying fortresses and liberators conducting high-altitude reconnaissance and bombing runs. For the first time, Japanese formations hesitated to intercept without numerical superiority. The strategic value of the B-17 thus extended beyond its bomb load. It redefined the balance between attacker and defender in aerial warfare. Each engagement forced opposing air forces to adjust doctrine, equipment, and expectations. What had once been mocked as excessive engineering now appeared as a rational response to industrialized, high-altitude combat. In February 1944, Imperial Navy intelligence received detailed reports from German flight test centers at Rechlin and Finnow. Captured B-17F and G models had been disassembled, weighed, and examined for material composition. Each assembly was photographed and catalogued. German engineers documented armor layout, hydraulic systems, and the SPEI electrically powered turrets. Japanese observers assigned to the Luftwaffe technical mission attended these sessions and compiled their own notes. The inspection revealed that American defensive technology relied on integration rather than singular firepower. The synchronization between the Bendix upper turret and the ball turret below allowed constant protection of vertical arcs. Twin-tail guns, set at an angle of 12 degrees, covered retreating interceptors. Nose-mounted cheek guns, introduced on the G model, closed previous blind zones. The result was measurable: enemy attack angles reduced from 12 to 4 viable approach paths. Photographs of the gun mount showed electrical wiring and servo amplifiers previously unfamiliar to Japanese technicians. The SPEI A-1A gyroscope stabilized sight compensated for aircraft movement, maintaining target lock within 2 degrees of accuracy during maneuver. German assessments recorded improved hit probability by 23% compared to manually aimed mounts. This data impressed the Japanese observers, who noted that similar stabilization technology remained unavailable in domestic production. The Americans also standardized ammunition feeding through continuous link belts, each capable of firing 500 rounds without reload. Gunner stations were designed with overlapping oxygen lines and interphone plugs, ensuring continuous communication under altitude conditions exceeding 25,000 feet. Japanese tests confirmed that such integration would require extensive re-engineering of existing bomber frameworks. By April 1944, the Imperial Navy's Aeronautical Technical Arsenal in Kugisho constructed partial mock-ups of a B-17 turret using captured components supplied via Germany. Technicians measured motor torque output and ammunition vibration resistance. Reports indicated consistent operation after 6,000 firing cycles. The test concluded that American electrical systems achieved a level of reliability surpassing available Japanese substitutes by a factor of 3. Parallel to technical investigation, operational analysis was conducted using post-raid data from Rabaul and WAWAC. Aircraft logs revealed that B-17 formations entering Pacific zones maintained formation integrity even after sustaining heavy damage. In several cases, bombers returned to base with multiple engines disabled or tail sections compromised. Imperial Navy reconnaissance photographs confirmed such recoveries. The intelligence branch compiled a table showing that 63% of damaged B-17s managed to land safely, compared to only 22% for Japanese twin-engine bombers. At Yokosuka, a small group of officers proposed adapting defensive turret concepts to future long-range bomber projects. Preliminary blueprints for a Japanese fortress-type bomber, later designated the Fugaku project, included powered gun stations and armor plating. However, industrial limitations and material shortages halted development before prototype completion. German liaison officers informed their Japanese counterparts of ongoing difficulties countering massed American formations. Luftwaffe studies concluded that each B-17's overlapping fire zones created a defensive network equivalent to a light cruiser's anti-aircraft battery. Japanese analysts translated this comparison literally: a formation of 20 bombers equaled the defensive output of a naval flotilla. Combat footage from the 8th Air Force raids over Regensburg and Schweinfurt provided visual evidence. Gun cameras recorded concentrated tracer density forming sustained barriers. Frame-by-frame analysis indicated an average of 12 firing guns at any given second within a single formation quadrant. Japanese officers studying the footage noted that conventional fighter attack methods, frontal dives or beam approaches, resulted in unacceptably high attrition. In May 1944, the Imperial Navy prepared an internal report titled Evaluation of American Fortress-Type Bomber Armament. It concluded that the B-17 represented a complete system where crew coordination, powered turrets, and industrial standardization functioned as one. The report recommended avoidance of direct interception without numerical superiority or altitude advantage. The document circulated among senior officers but produced limited tactical change. Many frontline units lacked the resources to adapt. Nonetheless, the study marked a turning point in understanding. For the first time, Japanese command recognized that the B-17's strength lay not only in engineering precision but in its embodiment of an industrial strategy, mass production of complexity sustained by logistics. The discovery phase closed with acknowledgement of technological disparity. Japan's wartime aircraft industry, optimized for agility and fuel economy, could not replicate the electrically powered, armor-integrated systems of American bombers. The B-17 was not a singular weapon but a product of a manufacturing ecosystem capable of producing thousands of identical, durable machines. The implications of this realization would soon influence Japanese assessment of the wider air war's trajectory. By mid-1944, Japanese military observers stationed in Europe submitted revised assessments to Tokyo. The Imperial Navy's Bureau of Aeronautics classified the B-17 as a strategic defense bomber, a term denoting an aircraft capable of sustaining offensive operations through self-protection. The terminology itself reflected an acknowledgement that conventional interception doctrine was obsolete. Analysts at the Yokosuka Technical Arsenal compared sortie data from Germany, the Mediterranean, and the Southwest Pacific. The average B-17 mission recorded 90 minutes of exposure to enemy fighters. Yet mission completion rates exceeded 85%. Cumulative records indicated that for every B-17 lost, 4 to 6 enemy aircraft were damaged or destroyed. These ratios suggested that the fortress did not merely endure air combat but actively reshaped its dynamics. Imperial Navy Air Combat instructors reviewed translated 8th Air Force gunnery manuals. The manuals emphasized precision bursts, controlled arcs, and teamwork across the formation. Gunner logs from the 303rd Bomb Group listed confirmed engagements, distances, and ammunition expenditure per run. The empirical data reinforced the same conclusion: defensive fire, properly coordinated, equaled offensive effect. Within Japan's combined fleet headquarters, this realization conflicted with existing doctrine that prioritized maneuver and surprise. The concept of static firepower contradicted decades of emphasis on light, fast interceptors such as the A6M0. When analysts plotted probability curves for gun coverage within a B-17 formation, they observed that overlapping fields produced continuous kill zones between 200 and 700 meters. Intercept trajectories crossing that band faced cumulative hit probabilities exceeding 70%. In operational terms, it meant that a single pass through a fortress formation carried greater risk than sustained dogfight engagements elsewhere. Japanese test pilots at Yokosuka simulated these passes using target frames mounted with flash sensors. Each attempt resulted in simulated hits within seconds. Flight instructor Commander Fumio Miyazaki concluded that only coordinated frontal attacks, supported by heavy cannon armament, might yield acceptable exchange ratios. By August 1944, combat experience in the Marianas confirmed the theoretical models. American B-17s and B-24s bombed airfields at Iwo Jima and Truk with minimal escort. Japanese fighters that attempted interception reported immediate casualties. After-action summaries from the 252nd Air Group recorded statements describing impenetrable defensive walls. Gunfire patterns observed from the ground showed symmetrical tracer lines forming grids around the bomber formations. Captured film reels from 8th Air Force cameras were later reviewed by Japanese intelligence analysts. They measured tracer density per frame and calculated an average of 1,800 projectiles per minute within each formation sector. This output equaled or exceeded ground-based anti-aircraft batteries of comparable size. The conclusion noted that defensive saturation replaced individual gunnery skill as the determinant of air superiority. The broader realization extended beyond tactics. Reports from industrial attachés in Germany described the logistics sustaining the B-17 program, factories producing standardized gun turrets, ammunition belts, and armor components across multiple states. Replacement parts arrived in Britain within days. Damaged bombers were repaired and redeployed in less than 2 weeks. Such resilience contrasted sharply with Japan's decentralized repair network and material shortages. Strategic planners within the Imperial Navy recognized the implication. If every lost B-17 could be replaced rapidly, then attrition-based defense was unsustainable. The true strength of the Flying Fortress lay not only in its guns but in the industrial system behind them. The weapon and the supply chain formed an inseparable unit. During September 1944 briefings, a senior staff officer summarized this understanding in technical language: firepower density per ton of airframe mass defines the modern bomber. His report circulated among research units but produced limited material response due to resource scarcity. The operational conclusion was clear: the Allies had achieved an integration of engineering, training, and production that Japan could not match. As subsequent raids intensified over the Pacific, Japanese pilots increasingly avoided direct pursuit of large formations. Tactical bulletins recommended climbing attacks followed by disengagement. The once dismissed Flying Fortress had become a symbol of aerial endurance, an aircraft whose guns transformed the sky into a measurable, sustained barrier of steel. This period marked the transition from disbelief to recognition. The Imperial Navy, after years of underestimating the concept, now regarded the B-17 not as an anomaly but as a demonstration of systemic warfare. Each gun mount, turret, and armor plate represented not excess but design logic, an economy of survival calculated through industrial mathematics. The realization was technical, undeniable, and final. By late 1944, Imperial Japanese naval analysts expanded their evaluation of the B-17 beyond tactical engagement. The focus shifted toward its strategic and industrial implications. Data compiled from German and American sources was consolidated into a technical monograph titled Airborne Firepower and the Industrial System of the United States. The document assessed not only the aircraft's design but also the infrastructure sustaining its production, maintenance, and deployment. Figures obtained through diplomatic intelligence showed that the United States Army Air Forces operated more than 12,000 B-17s by that period. Of these, approximately 8,000 were active in European operations. The remainder were distributed across training, reconnaissance, and Pacific commands. Monthly production rates at Boeing, Douglas, and Vega factories exceeded 300 units. The Japanese report compared this output with domestic aircraft assembly, which at the time averaged fewer than 100 heavy bombers per month across all facilities combined. Industrial analysis revealed further contrasts. The American system produced interchangeable turret assemblies, standardized ammunition belts, and pre-calibrated gun sights, allowing field replacement without precision adjustment. Maintenance manuals prescribed identical procedures across all theaters. Statistical appendices indicated that 72% of bombers damaged in action returned to operational status within 14 days. Japanese facilities, constrained by dispersed production and limited tooling, averaged repair times of up to 60 days. Operational doctrine amplified these material advantages. Allied mission logs demonstrated that B-17s operated in formations of up to 100 aircraft, each synchronized through radio frequency coordination. Defensive arcs overlapped, forming cumulative coverage exceeding 300 degrees around each bomber. Japanese analysts described this structure as a collective defense grid, equivalent to an airborne convoy system. The principle closely resembled naval tactics but executed in 3 dimensions. Comparative assessments with Japanese bomber forces highlighted the disparity. The Mitsubishi G4M and Nakajima G5N lacked powered turrets and armor protection. Crew survivability during interception averaged less than 20%. Statistical models indicated that, had such aircraft flown in the European theater, loss rates per mission would exceed 60%. The contrast underscored the technological and doctrinal gap between the two nations' air arms. By November 1944, the Imperial Navy's Aeronautical Technical Bureau began correlating B-17 performance with American logistics data. The analysis concluded that the aircraft's endurance and repairability stemmed from metallurgical advances, specifically, the use of Alclad 24ST aluminum alloy, which combined corrosion resistance with tensile strength. Samples obtained through German exchange programs confirmed this composition. Domestic substitutes, primarily duralumin, exhibited 15% lower fatigue resistance under stress testing. Japanese production engineers recognized that material science directly influenced combat effectiveness. The B-17's airframe tolerated repeated pressurization cycles and bullet perforations without structural collapse. Field measurements from recovered wreckage showed that individual panels could absorb up to 20.30 caliber hits before failure. Such data reinforced the conclusion that survivability derived from manufacturing precision, not isolated luck. Strategic modeling undertaken by the Imperial Navy Staff College projected the implications. If formations of B-17s could reach targets unescorted and sustain minimal losses, the operational value of interceptor fleets would decline sharply. This projection matched reports from Germany, where Luftwaffe fighter groups suffered depletion despite continuous reinforcement. By 1944, Germany required 4 sorties by single-engine fighters to down 1 B-17. The realization spread through Japanese command channels. Memoranda described the American approach as industrial warfare through the air. Each bomber represented not an individual machine but a statistical unit of a larger process. Its 13 guns were tools of deterrence, maintaining formation integrity until bomb release. In this framework, attrition was calculated, predictable, and offset by rapid replacement. The Imperial Navy's Internal Review Committee concluded its findings in December 1944. The final report stated, American air power derives from systemic replication. Firepower, logistics, and human training function as modular components. The committee acknowledged that replicating this model within Japan's wartime economy was unattainable under existing conditions. At that stage, Japanese technical officers no longer debated the B-17's merits. The debate had shifted to how its principles would influence post-war aviation. The Fortress-type bomber had redefined the parameters of air defense, industrial mobilization, and operational sustainability. Its existence forced every opposing nation to reconsider not only how aircraft fought, but how they were built, maintained, and replaced. By the end of 1944, these conclusions reached strategic command in Tokyo. The B-17 was no longer viewed as an engineering curiosity, it was evidence of an industrial system functioning as a weapon in itself. The Imperial Navy's final evaluation summarized it concisely: firepower is the visible component of production capacity. January 1945. The Imperial Japanese Navy completed its last formal analysis of the B-17 program. The document, marked highly confidential, technical reference only, summarized 3 years of observation and intelligence. It contained 122 pages of tabulated data covering airframe design, gun synchronization, operational endurance, and industrial replication. The conclusion was unambiguous: the Boeing B-17 Flying Fortress had transformed the nature of aerial warfare from individual combat to system-based engagement. By this time, American bombing strategy had advanced beyond the B-17 itself. Newer aircraft such as the B-24 Liberator and B-29 Superfortress extended range and payload capacity. Yet the foundational principles remained identical: crew coordination, self-defense, and standardized production. To Japanese analysts, the B-17 represented the prototype of the modern strategic weapon, a machine designed to integrate industry, logistics, and firepower into one operational unit. Post-war debriefings later confirmed how this integration functioned in practice. Surviving American airmen described training routines emphasizing mechanical familiarity as much as combat accuracy. Each crew member knew turret maintenance procedures, electrical fuses, and oxygen system functions. In effect, every bomber operated as a mobile workshop capable of limited self-repair during flight. This technical discipline allowed damaged aircraft to remain airborne when other designs would have failed. Statistical evaluation after 1945 verified these operational impressions. Of 12,731 B-17s built, 4,735 were lost to all causes during the war. Approximately half of these occurred in combat, the remainder through accidents or non-battle attrition. Even under sustained operations, the average loss rate per sortie remained below 5%. In comparative terms, the B-17 recorded one of the lowest fatality ratios among heavy bombers of the Second World War. Japanese intelligence officers who reviewed captured Allied reports after the war recognized a clear pattern. The Flying Fortress had embodied a philosophy opposite to Japan's aerial doctrine. Where Japan emphasized pilot skill and aircraft agility, the United States emphasized volume, standardization, and durability. The B-17's defensive network neutralized the advantage of highly trained individual pilots by creating statistical certainty through firepower density. At Yokosuka, a post-war technical review team reconstructed portions of their wartime evaluations. They verified that every component of the Fortress, hydraulic systems, self-sealing tanks, electrical circuits, had been optimized for function over form. The aircraft's appearance, once ridiculed as excessive and ungainly, now revealed itself as a product of precise calculation. The mass of armor and guns balanced perfectly with available engine output, ensuring efficiency despite complexity. Former Imperial Navy test pilot Lieutenant Commander Noboru Ueno, interviewed in 1946, summarized the reassessment plainly: "We laughed at it before we faced it. Afterward, we understood that it was not a plane but an industry in the sky." His words encapsulated the transformation of perception from mockery to technical respect. In the United States, military historians reached similar conclusions. Declassified Army Air Forces reports described the B-17 not only as a bomber but as a training framework for the world's first sustained strategic air campaign. Crews, ground units, and factories operated under identical technical standards. The aircraft's 13 guns represented the outward symbol of that uniformity, each gun maintained, calibrated, and supplied through the same logistical pipeline. The Imperial Navy's closing commentary, archived in 1945, acknowledged the broader consequence. The B-17 had demonstrated that firepower, when integrated with industrial organization, could achieve strategic endurance independent of territory. For Japan, whose wartime production relied on decentralized workshops and limited raw materials, the lesson was conclusive: air superiority depended on manufacturing capacity as much as aerodynamics or tactics. By the end of the war, few intact B-17s operated in the Pacific. Most had transitioned to reconnaissance or weather missions. Yet their influence persisted. Japanese engineers studying captured examples at Atsujai and Tachikawa noted that later American bombers retained the same system logic, modular components, standardized maintenance, and high-volume fire coverage. Post-war publications by the Allied occupation authorities later referenced these findings in Japan's aeronautical rehabilitation programs. Many Japanese designers who had once dismissed the fortress would later apply its principles in civilian transport and defense industries. The emphasis on redundancy, repairability, and crew coordination became standard practice. The final Japanese wartime report concluded with a technical statement rather than judgment. The Boeing B-17 Flying Fortress represents the evolution of air warfare from pilot-centered combat to mechanically sustained formation defense. Its significance lies not in its victories, but in its reproducibility. That sentence marked the end of the Imperial Navy's evaluation of the fortress and the beginning of Japan's recognition of industrialized air power as the decisive element of 20th century warfare. February 1946. Allied occupation authorities catalogued remaining Japanese wartime technical documents. Among them were complete translations of German B-17 intelligence reports and parallel Japanese analyses conducted between 1943 and 1945. These papers provided post-war researchers with a precise record of how Axis observers had interpreted the Flying Fortress. Their tone was analytical, detached, and increasingly admiring as the war progressed. At the former Naval Technical Arsenal in Yokosuka, American intelligence officers examined these reports under the Air Technical Intelligence Group program. They noted the detailed accuracy of Japanese measurements, including weight distribution diagrams and gunnery coverage charts. The Imperial Navy's engineers had calculated the fortress's kill probability per approach angle with near-identical results to U.S. Army Air Forces data. The convergence of independent analysis confirmed that the B-17's reputation was based on measurable performance, not wartime exaggeration. Technical debriefings conducted with surviving Japanese officers revealed a consistent theme. They had underestimated the importance of power-assisted turrets and centralized fire control. In interviews, engineers admitted that pre-war Japanese aircraft design had prioritized minimal weight and aerodynamic purity. The B-17, in contrast, represented a philosophical inversion. It accepted drag, armor, and mass as necessary trade-offs for survivability. The American solution used industrial strength to compensate for aerodynamic compromise. American analysts compiling the Enemy Aircraft Evaluation Report No. 112 in 1946 described this contrast succinctly. The Japanese approach equated maneuver with defense. The American approach equated firepower with survival. Both doctrines produced competent aircraft, but only one sustained large-scale strategic operations. Statistical tables appended to the report compared cumulative production outputs. The United States had manufactured over 60,000 heavy bombers between 1941 and 1945. Japan's total heavy bomber production during the same period was fewer than 1,400 units. The ratio illustrated the underlying reality: the B-17's effectiveness was inseparable from the system that produced and maintained it. Former German officers interviewed during Allied occupation corroborated Japanese findings. They confirmed that Luftwaffe interception losses against B-17 formations were disproportionate to expected outcomes. During the Regensburg and Schweinfurt raids, fighter attrition exceeded forecast by 35%. German test pilots attributed this directly to overlapping gun coverage. Japanese observers present during these debriefings noted identical conclusions in their own reports. Archival film analysis provided further evidence. Footage from multiple raids was replayed at reduced speed for ballistic mapping. Each 5-second segment revealed at least 10 intersecting lines of defensive fire within a single formation cell. Computed projectile density reached levels previously associated only with naval anti-aircraft barrages. Engineers at Yokosuka confirmed that no Japanese bomber unit possessed comparable defensive density or coordination. Post-war technical conferences held under Allied supervision explored potential applications of these findings for civilian aeronautics. Japanese engineers recognized that the fortress's electrical systems, redundant wiring, distributed fusing, and modular controls could serve as models for future transport aircraft. The emphasis on accessibility and maintenance shaped post-war Japanese aviation design, influencing early prototypes developed under occupation guidelines. American investigators also examined the psychological dimension of the B-17's defense concept. Mission records showed that formation integrity relied on collective discipline rather than individual heroism. Crews who maintained spacing and overlapping fields of fire achieved the lowest loss rates. Japanese analysts interpreted this as industrial psychology applied to warfare, a reflection of training as a process of standardization. The Japanese term coined in 1944, XAKB, structured defense, reappeared in post-war textbooks describing systemized teamwork in engineering contexts. Thus, a wartime observation evolved into a principle of organizational design. The fortress had become both a technological and procedural template. Declassified intelligence correspondence between American and Japanese engineers in 1946 further documented shared recognition of these systemic lessons. Former adversaries agreed that the aircraft's real innovation was not its 13 guns but its capacity to integrate human and mechanical functions with minimal failure tolerance. Each turret, relay, and intercom connection formed part of a single operational network. As Allied researchers compiled closing summaries, one recurring conclusion appeared in both Japanese and American reports: the B-17 represented the transition point from mechanical aviation to systems engineering. It demonstrated that complexity, when standardized, could achieve reliability at scale. This recognition bridged wartime adversaries into a shared technical understanding, an outcome neither side had anticipated during the conflict. By 1946, the Flying Fortress no longer served as a weapon. It existed as data, as a framework for post-war study, and as a benchmark for every heavy aircraft that followed. March 1946. The final phase of the Allied Technical Intelligence Review summarized the B-17's wartime influence and post-war legacy. In both Allied and Japanese archives, the aircraft appeared not merely as a weapon but as a transitional technology linking industrial mass production with systematic combat doctrine. The Imperial Japanese Navy's concluding memorandum, translated and filed under captured documents, reference 12-144 B-17, outlined this transformation with precision. It identified 5 enduring characteristics: structural redundancy, power defensive coordination, modular production, standardized maintenance, and psychological cohesion of crew. Each, the report stated, represented a quantifiable component of survival probability. American analysts reached identical conclusions. Reports from the Air Technical Service Command emphasized that the Fortress had standardized the concept of network defense. In its operational form, every gunner, turret, and formation cell functioned as a single data point within a broader system of predictive defense. This principle later influenced the design logic of the B-29 Superfortress, which incorporated centralized fire control and remote turret operation, direct extensions of the B-17's core philosophy. In occupied Japan, aeronautical engineers studying disassembled B-17 airframes at Tachikawa catalogued each subsystem. Wiring harnesses, relay boxes, and hydraulic actuators were diagrammed for reference. Many of these engineers later contributed to Japan's post-war civil aviation programs, applying lessons of modular assembly and reliability testing. Their report cited the Fortress as an example of design discipline achieved through manufacturing consistency rather than pilot performance. Industrial historians documented a broader consequence. The B-17 program had demonstrated that air power depended on reproducibility. The ability to produce thousands of identical machines with predictable results redefined global warfare. Japan's wartime aircraft, while often advanced in aerodynamics, lacked this reproducibility due to material scarcity and fragmented production. The contrast illustrated that technological superiority alone could not offset systemic inefficiency. In later years, American military archives declassified internal assessments conducted by the U.S. Army Air Force's Statistical Control Division. These analyses confirmed that the B-17 had delivered approximately 640,000 tons of ordnance during the war, with operational readiness consistently above 80%. The figures aligned closely with Japanese intelligence estimates made in 1944, validating the accuracy of their wartime research. From a strategic perspective, the B-17 marked the first global implementation of coordinated industrial logistics applied to air warfare. Japanese post-war defense scholars studying these operations concluded that the bomber's real innovation lay in its sustainment system, fuel supply chains, maintenance infrastructure, and standardized training pipelines. They described it as the integration of engineering and administration into continuous flight capability. Cultural perceptions also evolved. Wartime Japanese publications that had once ridiculed the American Flying Fortress as a mechanical excess were quietly withdrawn. In their place, post-war academic journals presented objective technical analyses. The tone shifted from skepticism to technical respect. The Fortress became a case study in systemic efficiency rather than national rivalry. By 1947, the term Fortress system appeared in Japanese engineering curricula, referring to any large-scale, self-sustaining mechanical structure operating under standardized procedures. The concept extended into industrial automation and logistics theory during Japan's post-war recovery. The same principles of modular construction and redundancy that defined the B-17 now underpinned new manufacturing methods. In American service, surviving B-17s transitioned into reconnaissance, weather observation, and air-sea rescue. Their continued reliability reinforced their legacy as durable, maintainable machines. When the last active B-17 was retired from the U.S. Air Force inventory in 1959, several were transferred to civilian use, testament to structural longevity conceived in wartime necessity. The Imperial Navy's wartime observers, many now civilian engineers, later reflected that their early mockery of the B-17 had represented a failure of analytical imagination rather than ignorance. They had viewed the aircraft through the lens of maneuver warfare, not recognizing that the future of combat aviation lay in sustained, organized systems. Archival cross-references compiled by Allied and Japanese researchers after 1945 revealed an unusual historical symmetry. Both sides independently reached the same final evaluation. The B-17 Flying Fortress had introduced the principle that air warfare success derived from quantitative coordination, not qualitative performance. The closing entry in the 1946 Joint Intelligence Summary recorded the assessment in neutral language. The Boeing B-17 represents the first generation of self-defending aerial systems. Its operational value exceeded its material composition. It proved that industrial capacity, when organized, can manifest as sustained firepower. Thus ended the analytical record of the Flying Fortress within Japanese and Allied archives. What began as mockery in 1942 concluded as acknowledgement in 1946. The aircraft that had been underestimated for its mass and complexity became the foundation for modern aerospace systems, proof that in the industrial age, precision, coordination, and replication had replaced agility as the ultimate instruments of survival.